Welcome. In this lecture, we shall look at the use of the double integration method to calculate the slope and deflection for the case of a cantilever beam. We shall initially consider the cantilever beam loaded by a single point load at the free end, then by a uniformly distributed load over the entire length, and finally with both loads superimposed. Let's start off with a cantilever beam loaded by a point load P at the free end. Let us show the reference coordinate from where the distance x of the section is measured at the fixed support. We may first need to find the reaction force and reaction moment at the fixed end for writing the moment expression at any arbitrary cross-section along the beam's length. Now, we write the bending moment expression from the equation of the elastic curve. It is given by m at x equals ei times d2y over dx square, and this equals p times x minus p times L. This is equal to p times x minus L. Integrating this once using the double integration method, we get the slope equation, that is ei times dy over dx is equal to p times x squared over 2 minus p times L times x plus a constant of integration c1. Integrating once more, we get the deflection equation, that is ei times y is equal to p times x cube over 6 minus p times L times x square over 2 plus c1 times x plus another constant of integration, that is c2. To find these unknown constants, we introduce two boundary conditions. The first of these states that the slope at the support, that is at x equal to 0, is 0. This gives the value of C1 as 0. The other boundary condition states that the deflection at the support, that is y at x equal to 0, is 0. We hence get the other constant C2 also equal to 0. The final equations for any cross-section along the beam's length can hence be written. For the free end, the deflection can be found out by inserting x equal to L. We therefore get the deflection as y equal to minus 1 over ei times p times L cube over 3. Minus sign indicates that the deflection is pointed downwards. The slope at the free end of the cantilever beam is found out as minus p times L square over twice ei in radians. You may note that the same result may be reached by reducing our calculations if we assumed the reference coordinate to be located at the free end of the cantilever beam instead of at the fixed support. Also note that though the slope values at the free end obtained by both the methods are the same, the sign differs. This is due to the fact that the reference coordinate system has been shifted in position and orientation. The second method eventually permits us to skip the initial calculations involving the reactive force and reactive moment, and also reduces the number of terms in the moment expression of the elastic curve, and therefore in the succeeding two equations. The selection of the reference coordinate system location is hence a matter of convenience. We now find the slope and deflection for the case of a cantilever beam with a uniformly distributed load acting over the entire length of the beam, assuming reference coordinate at the free end. We use the slope and deflection values at the fixed end equal to 0 as the boundary conditions to find the constants C1 and C2. The slope at the free end of the cantilever beam is hence found out as W times L cube over 6 EI, and the deflection at the free end as W times L to the power of 4 over 8 EI in the downward direction. Finally, we can superimpose the two loads together and hence the equations for the two separate cases together to get the respective slope and deflection values. In the next lecture, we shall consider the case of a simply supported beam loaded by a point load asymmetrically placed to find the deflection and slope using the double integration method and understand why it becomes tedious to use this method in general.